the last result last time. So Mg is a 4D non-compact shrinking Ricci solution. With bounded scalar curvature. S. So there are two statements. If the scalar curvature has behavior that it converges to 0 to infinity, then the manifold is asymptotic to a cone. And the second statement is that if the scalar curvature is not convergent, well, if it's bounded from below on M, then it's asymptotic to a cylinder. So quotient of the two possible cylinders. So I'm not going to talk about this at all today, because during the workshop I want to give more details about this and a more general result. So this will be next week. So I'm going to do only one. It's a sketch of proof. The details are not too complicated, so to fill out the details is not too hard. The idea is that you want to prove curvature goes to 0 very fast. So you only know scalar curvature goes to 0. You want to prove much better than that. So we know from last time that the curvature is bounded by scalar curvature. So therefore, if this goes to 0, then the curvature itself goes to 0. Then on the other hand, we know that the curvature tensor has an equation like this. And for the purpose of today's talk, I will ignore this one. And it's not such a bad thing to ignore it, because it's the square, right? So it goes to 0 much faster than this. It will not complicate the proof too much if you deal with this equation. So today, let's just ignore pretend. And it's not such a bad thing if you ignore that one. And so let's just pretend that you're not throwing away too much. From last time, I mentioned that 1 over f has a good equation. Again, this is true modulo some higher order terms. So this is 1 over distance squared. If you ignore higher order, like cube fourth, then this is what you get. And again, it's not a big deal to do the proof in general with square here and also with the error terms here. So comparing these two by maximum principle, you get that the curvature also is bounded by f. So the important observation was that if I know Riemann converges to 0, I mean scalar goes to 0, that forces the whole curvature tensor to behave nicely, then that forces actually to be even quadratic, right? So Riemann, it decays quadratic in the distance function. And then she estimates implies similar behavior for all derivatives. So, of course, last time I showed some better, even some better estimates than she, because I showed that this is comparable. It's bounded by scalar to the corresponding power. That one is better than. I mean, it's more general because in this context, because we are in that estimate, we're not assuming S goes to 0. We're just saying any shrinker has that property. So we know, so of course this is the kind of behavior you have in a cone, right? This is the curvature. And this is actually enough to prove it's asymptotically conical. Well, I didn't even say what that means. So of course the picture is it's pretty obvious, but what does that mean? So let me explain what I mean by that. I mean that there exists a manifold n-1 compact manifold sigma with a metric G with a metric G sigma on this manifold. So so what I want is the cone, the manifold, to be asymptotic to the cone, say 0 infinity times sigma. This is a cone, 0 infinity times sigma. The metric on the cone I want to be dr squared plus r squared g sigma. So that's the cone metric. So this has to be asymptotic to M, right? So in the following sense. So this is asymptotic to M in the sense that there exists a function from the cone. Well, it will be asymptotic at infinity. So this will happen outside the compact set into M. This is a diffeomorphism. So there is such a diffeomorphism into M, not the whole M, minus a compact set. So some part of the cone, some infinity of the cone is diffeomorphic to M minus a compact set. And then, with respect to the metrics, if I pull back the metric G by this diffeomorphism, and then I will rescale it. So this is how I rescale it. I will explain what this means in a moment. This is just the dilation. This converges to the metric on the cone. So I pull back this one here, I rescale it, I go to infinity, and as lambda goes to infinity, this converges to the cone metric, where I need to specify what rho lambda is. So for this in R and for this in sigma, this is just dilation. So you dilate, you go to infinity, you rescale. So of course it's a cone, right? So you have to rescale the metric as you go to infinity, and that has to converge to the cone metric. So it's not just saying that there is a tangent cone and it's smooth and so on. It's actually saying how you get it. It's actually describing it. And this sigma turns out if we know this sigma actually is the level set of the function. So I have a perfect description of the sigma. So let's be exact. So for us, what is sigma? So how do I construct this psi? How do I construct this sigma and g sigma? I will take.
So that's x plus the lambda.
Oh, sorry. So that was x. Okay.
Okay, I see this x. Or we just leave it there.
Okay. Right, so lambda is a real parameter that goes to infinity. So how do I construct this psi? How do I construct psi and sigma? I'll just take the flow of the potential. So say initially I want this to belong to be identity on the, so I want to float the level set at T naught. So this, by the way, was F equals T naught. That was notation last time. So I just want to start flowing a fixed level set. And it will just flow that into a corresponding level set of F. Right? So I'll just take this. And then I will construct G sigma by taking G tilde the pullback. So this is a metric on sigma of t. I pull back and I rescale. So I get a metric on T naught. So that will be a metric on T naught. And here we have a claim that this metric, this family of metrics on T naught converges as T goes to infinity in C infinity. So it's a C infinity convergence to some metric G infinity. So now once we get that, this will be the cone metric. This will be the G sigma. So that's all. So here you have to prove convergence. So I'll just show one step. You can take derivative in t. So that's one step, right? You take derivative of this, you get minus 1 over t squared. The other one, you get the Lie derivative so you get, again, phi star of the Lie derivative of G. Right? So it's not too much if I approximate this by T. It's not really D. It's right. Grad F squared is not F. It's F minus scalar curvature. But scalar being bounded, you get, when you do this approximation, you get some error terms which are higher order in T. They're like 1 over T squared. So it will not change the proof. So I will just say this is equal to and of course this is twice the Hessian of F. So that's G minus 2 Ricci. This with this will cancel out, right? G with G cancels out, so I get 1 over T squared. I forgot the phi star. Phi star Ricci. Right? So it tells me that if Ricci decays, then G tilde will converge very fast, right? So basically it tells me that since Ricci decays, it tells me that d dt of G tilde is like O of 1t squared G tilde. Right? So that's what it tells me. Because Ricci decays like 1 over t. Then that's integrable. So at least the point-wise you get some estimate, right? So you can integrate, and it doesn't prove convergence yet. It just proves boundedness. But you have higher order derivatives. So you know the covariant derivatives, everything. So you can use the sheet estimate. You get similar decay for all the covariant derivatives. So you can get similar decay for all the derivatives of G. So that proves convergence by Arzelà-Spoli. And in fact, not just that, it doesn't prove just that this converges. It also proves that you have even a convergence rate. That's 1 over t. So again, this is in C infinity because you can get higher order derivatives for G from the curvature information. So it does converge. You have this G tilde. This will be my sigma. Sigma will be the sigma T naught, where I have this metric. Actually, the cone the G sigma will be 1 over 4 G tilde, G infinity. So I do have the link of the cone, I have the metric on the link, so I have all the information. And now I just have to check that you do have that convergence through, right? So you do have this property. So you can check very quickly that if you do psi rho alpha, rho lambda of x is psi of lambda x and lambda r and x. I didn't say what psi is. So psi is related to phi, right? I want to take the cone and map it into the manifold.
You just level set to.
Right. So I just map the cone. I map the sigma into sigma T sigma. I map it into sigma of T, right? More or less. But I have to be careful because T on the cone, this has, let's say it's unit speed, right? Gradient is 1, but level set is not. So I have to match it. So I will map it into 1 over quarter r squared of x. Because the T is quarter of the distance squared. It's not distance itself. So this is what you have to do. So now I have the map. Obviously, this maps the cone into the manifold. It's a diffeomorphism. Now I just have to check what this means. So it's phi of quarter lambda square r square of x. Right? Now I just have to check what this thing star G means. That means phi times star G, phi star G. If I want to divide by lambda, I will divide by lambda squared. So this is very related to G tilde, right? It's exactly G tilde, but not, I still have to divide by 4 over r squared G tilde of, right? So it's by the definition of G tilde here, I have exactly that. I'm wrong. It's r squared over 4. And this converges, as we know, as we proved there, it converges to r squared over 4g infinity. And my definition was that 1 over 4g infinity is g sigma. So that's why 1 over 4, because of this 4 from here. So that's exactly checking that on each level set, you know that the convergence is true. Then you can do it for arbitrary level. You can do it on the whole manifold as well. Okay, so that's the proof. It gives you a very clear description. So it's not like you have a cone and you don't know where it comes from. It's really the link. It's just a level set of the manifold, and also the metric on the cone comes from the metric on the manifold in a very clear way. So you can everything is very explicit and unique for the manifold.
You have the geometric estimate for the cross section for the matrix.
Yeah, everything right because of the curvature information and the definition of phi, you do know diameter, volume, everything. Right. So you just do first variation. I mean, you do ddt of g, right? And you use the Lie derivative and so on. So. Right. Now, of course, I'm not including all the details, but it's because of this information and because the definition of phi, so it's given by the gradient of f. The derivative of that, the Lie derivative, is known. It's 1/2 minus g. So 1/2 minus g half minus Ricci, and you know Ricci how it behaves. You know the derivatives. So yes.
If the curvature S means boundable by c divided by r squared, does she has S?
Right. So this implies this one.
If you don't have 1 plus 1, you do not.
Oh no, but of course this is a smooth, right? Man. So of course this is behavior at infinity, right?
Well, outside compact set.
So it's a behavior at infinity. It's not a problem inside.
So are you saying the limiting metric has positive Ricci?
The limiting metric is not known if it has positive Ricci because of the rescaling. It has bounded curvature, but even that is not. We don't know if it or uniform bound. So we don't. I mean, we have no idea what.
But just I may lost somewhere. So how you will see the diameter is less than part of the limiting metric?
So you mean are you asking if I know a uniform bound for the diameter of the link?
Yeah.
So I don't know if it's uniform in the sense that if it depends only on dimension, but I can prove a bound, but depending on this C.
Oh, but you can't say it's less than pi. Oh, less than equal to pi.
Oh no. I cannot say exactly. I mean, I can say it's bounded by some constant, but that constant comes from here, not. Right. It's not some universal constant. Or I don't know how to prove it's a universal constant. Yeah, so I misunderstood your question. So everything comes from here, but these estimates are rough, so we don't know C. So the only thing that we can prove is that in the Kähler case, the link is connected. So there's only one component.
It's more or less, maybe I need some, more or less it's like a kind of a special work product, like Euclidean work product, but it's not like a cone.
Oh yeah, so a cone in this general sense, that it's basically a cone over a Riemannian manifold, three-dimensional Riemannian manifold.
Some compact set.
Yeah. So it's not cone in the sense that it's not the metric. We cannot prove that it's S3. So
it's not rotational. It's not rotational like Euclidean cone.
If you think about the right.
Yeah. So okay.
Yeah. So with this result, I want to describe that we can hope for a classification of 4D shrinkers, non-compact ones. But of course this is just very far at this moment, so it's something in the future. So we know how more or less in these special settings of I erased here, but there were two cases and we know the asymptotic geometry. So we would like to prove uniqueness. If we can characterize, but this is related to your questions, we don't know yet anything about the link, about the cone, or even curvature positive. So even if it's diffeomorphic to the sphere, we don't know yet. But hopefully we will get there in the future. If we do get there, there is a theorem by Kochwar and Wang. So Lu Wang. which says that if two manifolds have the same asymptotic cone, then they must be isometric to each other. So if I'll just state it in dimension 4 because this is the setting I'm interested in, but the result is true in general. So I'm assuming, let's say, that scalar curvature goes to 0, and they do have the same asymptotic cone. They are asymptotically conical, and they do have the same asymptotic cone. Then they must be isometric to each other. So then this is good. We just have to work and find out more information about the cone. It's not trivial. It doesn't seem very easy, but any kind of new information that will tell you more about how many shrinkers you have in dimension 4. So I'm just going to describe for the rest of this lecture. I will describe idea of proof. It's a long proof, but the idea itself it's not too bad. Just that the details, filling out the details is complicated. So the idea of proof is to think of this as Ricci flows and to understand what the cone means as for the Ricci flow, right? So if this is the first step, if MGF is asymptotically conical, say with cone say 0 infinity with product with sigma and G cone, so we know it's asymptotic to this cone, then there exists a Ricci flow on not necessarily on the whole manifold. I'm not interested in that, but just on outside the compact set. So there exists a Ricci flow. I'm not going to call it T. I'm going to call it S because T is already used there in a different way. So let's call it S. S is between, say, 0 and 1. So there exists a Ricci flow on outside the compact set, so that as S goes to 0, as S goes to 0, I want to say 0 and -1. Sorry about this. So as S goes to 0 increasing, I was confused because I think yesterday I did minus infinity to 1, so this would correspond as S goes to 1. But I would prefer to do it with 0 today. So there exists a Ricci flow from -1 to 0, and as S goes to 0, the flow G of S converges to the cone metric. Outside this compact set. So the convergence is outside the compact set, and it's smooth. So we are removing the tip of the cone. We are removing a region in the cone, so then the convergence is smooth. So this is why this is true. So the reason for this is because when you look at the flow. So just the intuition behind this is that when you look at the flow is, this is a self-similar solution. So you're just flowing points around. What it means, you're going to infinity, and then you're rescaling your solution. That's what the flow does, right? If you remember, it was something like minus S phi S star of G, right? This was G of S. So you go to infinity, and you're rescaling. This rescaling is by a small factor, right? You're scaling down. If you look at that definition, that's exactly what you're doing, That's why I prefer not to use t, because I want to compare that. It's also going on the level set towards infinity and then scaling down. Well, if you check the details, you will see that the two are not really identical, but they're very close to each other, the two things. So that's why you have a Ricci flow that becomes, it's singular at 0, but if you look outside the compact set, it's actually smoothly convergent towards the cone. So the problem is therefore a uniqueness problem. So treat this as a backward uniqueness problem. For the Ricci flow. If you know that you have dg over dt is minus 2 Ricci, right? And we know g of 0, right? So this was for, I would say s to be consistent, s between 0 and -1. And we know g of 0. Does this determine g of s? Right? So if I have two metrics with the same g of 0, can I say the metrics were the same for all times, for all previous times? So that this is the question. If we can say that, then g of -1 is exactly the soliton metric. So then it's determined. So this is the question. And the prototype. So and this is easier to explain actually. So for the details for this are easier. But the prototype is a theorem by Escauriaza, Seregin, and Zverak. And it's in Rn. So it's the prototype is something in Rn, but it works very well for manifolds as well. So instead of doing backwards uniqueness for Ricci flow, I'll do, or backwards uniqueness for a heat type equation, we do forward uniqueness for a joint heat equation. So we'll look at d tau. So instead of dg ds is Laplace of s, or Laplace of g, I'm doing backwards. So I'm putting plus here. So if this is true, so this, I have this estimate. It's not necessarily backward heat equation. It's just maybe controlled by some epsilon. And this is true on Rn minus a ball of radius r. So exactly like here, I don't know the flow exists for all the manifold. I know only outside the compact set. So this is outside the ball. And I know that the function doesn't grow too fast. So it grows at most quadratic in the distance. Everything is on Rn minus that ball. So the function may not be defined everywhere. So at the initial time, the function is 0. That corresponds to final time for the heat equation, but this is backwards heat equation, so initial time is 0. This is true, I'm sorry, I should have said for all t between, or tau between 0 and t. So it's true from 0 to t. But 0 has the significance, it's backwards, right? So 0 has the significance of initial, and now t is the final. So it's kind of like -1, t would be 1 in my case. So if I know initially it's 0, then this they prove that u must be identically 0 for all time. So you must have a solution that's identically equal to 0. So of course it's a long proof to explain. but I'll attempt to give you the idea behind this, and then very quickly to see what's the difference on a manifold case. So the idea not for this proof for the Cauchoir-Wang, but for the theorem in Rn. So the idea is the so-called Kahneman estimates. You take two functions g and f, defined with compact set, maybe not necessarily compactly supported, in Rn minus the ball. So actually, maybe I will assume for now that U has compact support. So let's assume. So let's suppose that it has some compact support, and then we'll deal with the case when it doesn't have compact support. So let's assume I can integrate by parts. It's a long formula. Then we have the following. So bear with me for a second. I think it's an interesting idea, and then later today in the second talk we do steady, so you'll see a different kind of argument how to prove such uniqueness. And they're kind of exclusive. It seems like they don't work. One setting doesn't work for the other. So this is the formula. The integration is everywhere in Rn. So it's not it's not t yet. I'm not integrating in t yet. And where A means the following. And where phi is log of g. So this is the important identity, and it's true for any function. Any function g, any function f, we have this. Which one? Yes, that is correct. It has negative sign. So you just integrate and you see this is true. So the way I would start, there's a maybe deeper idea why this is true, but the way I would start this formula would be just from the middle term here, and then expand. When you do AU squared, you do AU with this thing, and then with whatever is left. Then you integrate by parts until forever, and then you get the formula. So it's just a computation. But now the question is, so what? So how do we use this? The reason we like it is we have a lot of freedom in choosing this phi, right? So on one hand, since you asked, we want to get rid of this thing. So we take f to be g tau minus Laplace g over g. That because this term is too bad. So now I can just ignore this here. But I didn't want to tell you straight from the beginning that f is this, because then maybe it's where does it come from? It comes from that identity which is true for any f and g, and you want to eliminate a bad term. Then, why is this useful? It's useful because this is positive. So Cauchy-Schwarz, you can bound this guy by this guy using Cauchy-Schwarz, right? Then you have AU squared, and then you have this one. But that one is known to be small. So what you do get in the end by using Cauchy-Schwarz, you get 1/2. And let's integrate in t as well. So this is clear so far. I'm just picking up the terms that I have left on the left side, and then those two on the top, again, you can use Cauchy-Schwarz, and they amount to this here. And you integrate by parts and so on. I mean, you use, not integrate by parts, you use that formula, and then integrate this one from 0 to t. So all it's left it's the formula at capital T. Why not at 0? Because u is 0 initially, and then this term is negative. I mean, this term is positive, but at 0 will be negative. You have from 0 to t. G will be a positive function, so of course I want G to be a positive weight. G is a positive weight. So I only have this information at capital T, which may be a problem. So at capital T, we have to check how to get rid of this. Okay, so that's the problem. So now, what the f and what the g and f and phi you take? Well, it depends. There's not necessarily a unique choice, right? So it depends on what you want to achieve. So let's look at the following g. So this is the choice for G. And I can explain very quickly why. Because phi is log of G, right? So it's this part plus x squared, right? In terms of computing phi ij, this part is insignificant. It's linear. So the quadratic part is important, but that's greater or equal than delta ij, right? So of course, because I need to throw something away from here. So this part, it's good. This is greater or equal than twice gradient squared, which absorbs the epsilon. So that's the good part. It absorbs the epsilon. Then you have to compute a lot. You take g from here. You compute g tau minus Laplace g over g. And then you have to compute that. That will be f. Actually, f will be negative. So it turns out f is negative. I can ignore this term. It's negative. So I can throw that away. But you have to compute f tau plus Laplace f. If that's not positive, then you are in trouble here. It turns out that f tau plus Laplace f is greater than 1. Then you can absorb, this one will be bigger than u squared. So you can absorb the epsilon there into the left side. The question is, what do you do with the gradient? That you cannot absorb in anything because it's at final time. However, g at final time this becomes 0, so it's just e to the x squared, right? So, okay, I cannot prove that I can absorb the right hand side into left hand side, but I have an alpha here which is unaccounted for. It is true for any alpha, right? So then you make alpha go to infinity. So that if you make alpha go to infinity, this thing is positive. It will go to infinity for any earlier time. So you do get that u and gradient u and everything must be 0. Okay? Again, it's because this one does not depend on alpha. It's a constant. It's c. But this left-hand side, which absorbs the right-hand side, does depend on alpha. And actually, it goes to infinity and when alpha goes to infinity. So that's why. However, this is only half of the proof. The reason it's only half of the proof is because u was not with compact support. U was only defined outside that ball. So if it's a compact support, this would be the proof. But it's not. So you must have cutoff function. You use a cutoff function, but the cutoff function gives you terms on the boundary. So there are two boundaries, at infinity and at 0, and at r, sorry. So I said outside the ball of radius r. So there are two cutoff functions. One is at infinity, one is at r. The one at r, you can, all the terms coming from r, you can get rid of them exactly like here. Because when you're close to r, alpha, this thing is very small. When you're further from r, this starts to become huge, right? So when x is r plus 1, then already you have e to the alpha. So that's how you can get rid. So this is the magical part. This becomes small either when you're close to the final time, which we used here, or when you're close to the boundary, which you use when you use a cutoff. The other issue is that you need a cutoff at infinity. This grows like x squared. So what I did here would prove the theorem if you would replace the growth by minus here. If you would replace with minus, this would be the proof. That's all. So it's a one-page proof. If you replace, but you don't know. They want to assume even that it's growing very fast, not decaying very fast. It's growing exponentially, not decaying exponentially. So then you have to use a different argument to prove that if it grows exponentially at most, then it also decays. Or it's bounded, right? So then, decays exponentially so that you can use this part. This would be, in their proof is the second part of the proof. The first part is to use similar argument to prove this implies the decay. So there are two Karleman estimates. The other Karleman estimate is trickier because G, you must take it with minus here because that's the kind of behavior you have over there. You know it's exponential. If you take minus, that creates a problem here where you have phi. It's negative. So this argument won't work, right? So then you have to do something else. You introduce another function. So you add, besides G, you add another function which creates more positive terms. So philosophy is the same, different G, let's say, different functions. Okay, so it's a purely PD proof, and it's integration by parts really. So it's just that's the identity that it's important, and once you have it, it works. So now let me explain how this follows from this. So because this is a Ricci flow, and this is a heat equation in or heat operator in Rn. So this is the part from Rn to the manifold, right? To the shrinking case. So what is the difference? Because we have seen a lot of equations which look like this, right? Or dt minus Laplace, so that becomes d tau plus Laplace of Riemann equals Riemann squared, and all these things. So what is u in my case? This is actually a little tricky. So you are tempted to do, this would be the most naive and probably, maybe it's so naive that most of you would not think about this, that it would work. You take u to be g minus g bar, right? So you have g and g bar, two Ricci flows. And initially, finally, at t, in my case, t is 0, right? They're equal, they're the same, sorry. So they're the same. So the two Ricci flows are the same at final time. Let's say, this one I want backward Ricci flows. So I have two backward Ricci flows, and at final time, they are the same. At initial time, they're the same. At time 0, they're the same. So I want them to conclude G and G bar are equal to each other for all tau. They're equal to each other for tau 0. So tempted to say maybe U should be G minus G bar. D tau of G is, or plus Laplace of G 0, right? This is because Ricci, or minus 2 Ricci, as we know, is Laplace, right? Of G. Right? So minus 2 Ricci is Laplace of G. So I have a backward heat equation. Looks like we are in good shape, but it's not really that, because this is Laplace, like Jacob said yesterday, so it's basically Laplace of the ambient metric of G. So you cannot take G minus G bar and say there's some Laplace for which this is true, right? So that won't work. You have to do much better than that. So actually, this is earlier work by Brett, where he finds a closed system. There's a closed system of equations. That won't work. So the closed system of equation is to take rho to be Riemann minus. So you have to involve everything, not just the metric. You have to involve the difference of curvature. This is a 3-1 tensor. Then you take t to be the derivatives, the difference of derivatives. Then you take, there are many others. So you take u to be g minus g bar, v to be gamma minus gamma bar, that's also a tensor, and w to be gradient of gamma. Right, so these are the Christoffel symbol. They're not tensors, but take the difference is a tensor. So you take all these things, then you take the sum of the tensors. So Brett used this in a different context, but still related to uniqueness of the Ricci flow. So if you do this, then actually they do form an equation, a system of equation which is very similar to the one before. So this is very similar to the one we had before. So if you compute d tau plus Laplace of the curvature and the covariant of the curvature, then you can estimate them in this way. How does this work? You just compute, you have the equations for curvature, but this is for Riemann bar, this is the Laplace with respect to G. So you have to transform Laplace into Laplace bar. For that, you use V, right? So that's why you get the X and also the Y. Y amounts to the difference between connections. Then you also want to compute something for Y, but this is an ODE component, not a PDE. Oh, sorry, this is this one. So long story short, and I'll finish here. This is what replaces the U. So U will be actually X plus Y. And it kind of verifies the same system. Where does the epsilon come from? So the epsilon here comes from the fact that the curvature goes to 0 at infinity. So you throw away whenever you see Riemann square, right? You compute Laplace dt plus Laplace of Riemann is Riemann square. Whenever you see Riemann square, you throw it one Riemann away, that will be epsilon, and keep the other Riemann so that you have X. And that's all, right? So basically you replace, this setting with that from function to sections of bundles, that's all. But you have to come up with this closed system of equations. There are other small things that you have to be worried about. When you integrate by parts here, it's easy. It's Rn. When you integrate by parts here, you get Ricci identities. All of those being small because curvature is small. So again, you include them in the epsilon. So that's fine. What will be the x squared? You have x squared over there. What will be the x squared? You have such a nice potential f which behaves like x squared. So you use the f. You know everything about f. You know the derivatives, everything. So everything goes through, but with a lot more work and more details. Right? So it's a bit more inconvenient, but the idea is the same. Okay? So I'll finish here and then start the last part about steady solitons in a few minutes. Yes?
This F coordination is for Ricci flow. So what is the F?
Again, once you have a soliton that's asymptotic to the cone, basically you forget F, you forget everything, and you think of a Ricci flow which at 0, right? Two Ricci flows which are the same at initial time. If you ask me about my last comment that you have F here, well, it's because it is a Ricci flow, but you still have the F, right? The Ricci flow is defined by scaling and the gradient flow of F. So F is always there. So if you want to prove this for arbitrary Ricci flow with curvature going to 0 at infinity, it won't work because you don't have that function. The function comes from the soliton. A lot of the details probably work if you just assume Ricci flow with curvature going to 0 at infinity. That's good enough. But how do you construct that function? You can't just take distance squared because that's not smooth and you know nothing about it. You need to know Hessian, right? You need to know that this is true, right? So how do you compute it on an arbitrary manifold? This would never work for steady, for example, because you don't have such function on steady or expanding for that matter.
Well, you have function, but
it's not good.
Nice.
It's not good.
Yeah, it's in a sense F will be
So right. So maybe I'll talk about this in the last lecture because I want to talk a little bit about steady.
So you replace the x squared by F, right?
Here in this proof, yes. In steady, you might want to replace by F squared, but you don't know if the Hessian is positive.
Well, even you assume, say, Sim-Brand case, section of curve which is positive, right? Whether that
but it doesn't tell you that the Hessian of F squared. Yeah, probably that's tricky.
Curvature decay maybe not fast.
And so for steady, I think for me the biggest challenge, if you want to implement this, is that is not just time zero, you have to rescale the manifold as well, right? So you know it converges to cylinder, but after you rescale the metric. Here there's no rescaling of the flow. Here is just the flow initially. So not a rescaled version of the flow converges, but the flow itself. So I'm not saying they don't say it's not possible, they say it does not seem possible. So
The techniques at least.
yeah.
So in this case, if the curvature decreases quadratically, but of course you don't have the function, if you just have Ricci flow, that's
Right.
the only issue.
So this part, of course, works. It's not using any soliton business, and then a lot of it works until the last part where you have x squared.
Cauchy has the result that you have backward uniqueness, non-complete
Right.
manifold.
Exactly. By this is just you use this Gromwall stuff, and it gives you the uniqueness. I mean, right. That's how he does it.